Give me a second. Do you see the slide now? Noise and interference limited links. You do, right? Do you see?
Sir.
Do you see the screen? Do you see the slide? Guys?
Yes, yes.
Okay, okay. So on the right side, you have noise and also interference. The well, on the left side, I don't know how much uh, how much you could hear. On the right side, there is a maximum distance, and the CNR C by N will degrade as you go further from the transmitter, and so at a particular distance, you have the minimum C by N permissible. Okay, how you set the minimum C by N? Depending on the receiver capabilities to provide some minimum level of BER, okay, which is called the receiver sensitivity. Based on the receiver capability, you set a minimum C by N, and that sets the maximum distance possible for your receiver. In the case of interference limited implementation, you reuse. So you have another source and the transmitter shown in red, and the transmission from there you consider interference. Okay, it is undesired. So as you are going further away from your presently serving transmitter, you are also getting closer to other transmitters, to the transmitters who are transmitting at the same frequency. Okay, so your carrier power is degrading because you're going further away. On top of that, you have the interference increasing, okay, as you're getting closer to the other source, transmitting at the same frequency. So it is affecting you in both ways. And don't remember that you also have some noise. The noise level is shown here. So in addition to noise, you have two effects: the degrade of carrier power and the increase in interference power. So as you're moving further and further away, you calculate C by CINR, okay, considering all of them, and at a particular distance, the CINR may have the minimum permissible value, again considering your receiver sensitivity or how the level of CINR that can the receiver can work with for a minimum level of BER. Okay, so this is a baseline discussion. Here the noise is shown to be, the way it is shown does not relate the practical values. Okay, the practical carrier or interference powers are much higher than the noise level. Okay, so but anyway, this shows the how the different values are actually combined. Questions? Questions? Okay, let's talk about our lab class. Well, how many weeks are you left with after Eid vacation?
স্যার আমাদের ফাইনাল পরীক্ষা 30 তারিখ থেকে 30 আগস্ট
30th August. 30th August. Okay. And when does the class stop? Do you remember?
একটু চেক করতে হবে স্যার।
Okay, but looks like we have sufficient time. Yeah, so I think we can manage. We can manage after Eid. But do you really need that? Do you really need having the lab class after Eid, or I mean, in the classroom, there are some proposals to have the lab class after Eid. Do you all agree with this proposal? I don't hear you. Uh, do you all agree with the proposal that we should have the lab class after Eid?
Yes, sir.
Okay. Okay, then we'll have it after Eid, inshallah. Then in this current week, there is no class, of course. And so in the next week on Wednesday, we'll have our lab class. So that will be 28th of 28th of July. Okay. So on that day we'll have our next lab class. Okay. Now I will talk about modulation and coding. And actually their adaptation, okay, with the variation of radio link. In the case of non-LOS links, and especially when you have I'm sorry, when you have mobile environment, the user position, as the user position varies, the radio link quality changes. Okay, give me a second. And as you have a variation in the radio link quality, few things should be adapted. Okay. Well, okay. The early slides here will explain the digital modulation, and these things I think either you know already or we touched upon before. Okay. Digital modulation, this ASK, FSK, PSK, we probably touched upon before, right? Or you know already. I won't repeat this discussion if they have been covered. You know these things, right? What I'm showing. Do you see the screen? 8 PSK now, then 4 PSK or QPSK. You're familiar, right?
Yes, sir.
Yeah. Okay. I mean, did I discuss them in the class?
No, sir. No, sir.
I did not. Okay. Okay. So anyway, you know that a symbol, which is also called baud, okay, symbol rate or baud rate, tells you. I mean here, there's an example to convert the baud rate into bit rate, probably. Okay. Anyway, so ASK, FSK, PSK are the basic classes, and a combination of ASK and PSK is COM. Yep. Where you can have, like, this is an example where you can have both the variation of amplitude and phase in the constellation. Okay, these things are called constellation diagram. Okay, now this is how you transmit. from the transmitting end. If it is a wired transmission, then there is not much interference. Okay, CINR will be good. So the receiving end, the constellation diagram, okay, I mean the position of these dots in the constellation are not much deviated. You have pretty good replica of the same positions in the constellation. What I mean that the relative amplitude and phase values, okay, for the different symbols are held with pretty good quality, or I mean the relative values don't change much if you have good CINR. But when you have noisy environment, or I mean interference, I mean poor CINR, then these relative positions uh, can be lost to some extent, or a dot can have a hazy area around itself at the receiving side. Okay, I saw it in our test lab in in USA. On the receiving side, we had a signal analyzer. Okay, so on the transmitting side, there is a display showing the constellation diagram of what we were transmitting. Okay, it was a transmission for WiMAX signal there. So I mean, these things are called base station emulator, BSE. Okay, which simulate a base station and work like a base station, and it also transmits signals, but for testing purpose. Okay, so at the receiving side, we had a signal analyzer. So when it captured the signal, I mean, so environment is created to simulate the practical field. So what we had at the receiving side had a lot of deviations in the constellation diagram. So some hazy area around the dots. Okay, so this can give rise to some misdetection. Like if you have, say, uh, consider any of these diagrams. Okay, maybe say if we look at the rightmost one, this 16 QAM, two amplitudes, 8 phases here. Okay, so if a dot moves, say, towards right to some extent, then the receiver considers the symbol content depending on its amplitude and phase, right? So as we can see here, its phase and amplitude tells you what bits you have inside. So if it is a little bit shifted, then the receiver can be confused. If it is quite a bit shifted, then there is a chance that the receiver will consider that the actual position may be what you have at the, what you have for the next dot. It may confuse, okay, it may misdetect the position of the dot. So if it considers a different position, it also considers some different content for the symbol. Consequently, you have some misdetection of bits. Some zeros can be detected as ones, or ones can be detected as zeros. Similarly, at the levels of amplitudes, okay, the hazy area or some deviations from the actual position in the constellation diagram of the receiver can confuse and lead to misdetection. Okay, so misdetection of the position in the constellation diagram, or in other words, misdetection of the bit content of the symbols. So these are the issues that engineers need to work with, especially when the CINR is poor. If the CINR is good, then they can keep their positions pretty well. Okay. So wireless environment is, when you have non-LOS on wireless environment, then you have poor CINR, and especially the cellular example is the worst, or you have very poor CINR. Okay. Well, here I am actually defining BER. I have already defined it. It's called bit error rate or bit error ratio. Okay, both mean the same, BER, and this is how exactly the way you can calculate. I already told you that you take a ratio of the number of bits in error and the total number of bits that you have sent. Okay. Oftentimes you can show them in percentage. Blur means the packets, the bits are always packetized in digital communication. Whenever you use the bits are always packetized for transmission. So for at the lower level of packetization, there are also different levels. This is called protocol stack. We did not discuss it before, but we will inshallah touch upon it later. So at the lower layers, when you have packetization takes place at different layers. You may already know that IP packetizes, and this IP packet. Okay, so at different layers there can be packetizations. When you have packetization at lower layer, which may be the MAC layer, okay, then it is called block, or it may be even in the physical layer. Okay, so either physical or MAC layer has which is the layer 1 or layer 2 packetization is called block. And if you count the number of errors in terms of blocks, okay, that how many blocks have erroneous bits compared to the total number of blocks transmitted. Okay, not exactly how many bits are in error compared to the total bits. Then you can call it blur. Okay, blur. Its synonym is PELR, where you can packet error loss rate. Okay. Now, that's the problem. BR or blur is the estimation of the level of problem. But how we can circumvent, how you can overcome the problem. There are, methods like error detection. Okay, and also there are methods like error correction. In the case of error detection, you cannot correct. You just find out which packets are in error. Okay, like to calculate blur, you need to understand that some bits are in error there. How you can determine. For this purpose, you can use some methods, and two of the common methods are cyclic redundancy check, CRC. I'm sorry. And checksum. The calculation for these methods are not too difficult. For CRC, I did this computation by hand. It's not, too difficult. Any of you can do that. You just need to follow some fixed steps. But with that, what do you do on the transmitting side when you packetize? You calculate a few bits considering or based on the total bit stream in the packet. The bit stream in the packet is a combination of ones and zeros, you know. So based on that, you compute a few bits using a method called CRC or a method called checksum. Okay. And these few bits you add as a header field, okay, or as a field at the tail of your packet. Okay. A separate field is added to the packet, which contains this information, CRC bits or checksum bits. The receiver performs an opposite calculation to check whether or not these CRC bits match the whole content of the packet. If they match, then it knows that all the packets of the all the bits of the packet have been correctly received. Okay. And if these checksum bits or CRC bits, when calculated with all the bits in the packet, don't match, then it is realized that the bits are not, all the bits are not correct. But it doesn't know which bits are in error in the package, or it cannot even correct. Okay. I mean, if it knows that which bits are in error, then of course it can correct, but there is no clue which bits are in error or how you can correct the bits. Okay. So you just detect that, I mean, detect whether or not a particular packet has some erroneous bits. That's it. Okay, but how it can help you? Shortly, I'll tell you. Before that, let me show you that there is a stronger method which is called error correction, where it is forward error correction. It is called forward error correction. I mean, well, uh, the way we want to put here, okay, um, is that okay, I'll go from here. So how it can help you, I'll tell you now. When a packet is found in error, the receiver can send a feedback to the transmitter that this bit has not been received correctly. The transmitter will then retransmit the same packet. Okay, meaning that right after the transmission, the transmitter does not discard the packet. It keeps it. The receiver receives and checks whether it is correctly received or not. If it is correctly received, it can send a feedback that it is correctly received. And thereafter, the transmitter can discard. And if it is not correctly received, then the transmitter can resend. Okay. So once its reception is confirmed, the transmitter can throw it away. This is called packet retransmission. And this can help you overcome the errors in the packets. But this is definitely an expensive method. You have to transmit the same packet. Okay, so that adds some bits. Okay, right? I mean, the total capacity of bit rate you are using for transmission, but some of the packets you are retransmitting. So the overall data rate will actually degrade, right? I mean, just assume that if every packet is retransmitted, every packet is transmitted twice, then the actual data rate will be half of what the capacity of the link is, right? The actual capacity may be, say, 100 packets per second. But if every packet is retransmitted, then the actual transmission will be 50 packets per second. So packet retransmission can correct your reception, but it has some drawback too. I mean, nothing comes without anything. I mean, nothing comes free. So that is why what we are showing here is the second option, retransmission of the erroneous packets. When the packet errors are detected. Okay, detected maybe using CRC or checksum. The first one is forward error correction, where you can correct in one shot. You don't have to retransmit. You're transmitting, and in this same forward link, forward transmission, okay, or one-way transmission. Forward here, forward terms means that from transmitter towards the receiver. In this forward transmission, you don't only transmit, you also correct your transmission. This is called forward error correction, or FEC. And how you do that? This is nothing but channel coding. Okay, yeah, well, probably, I mean, you guys are very expert at making. I mean, I'm saying it because we have a real expert in channel coding in at our university, Professor Dr. Rakibul Islam. He has worked a lot in this area. Okay, so if you have got any coursework or some other activities with him, then you must have very good idea about different coding schemes. So where you, oh, sorry. So far you haven't got any course with him, right? You have not.
No, sir, we got
Sir, we
TNP
got
course.
one,
Yeah,
but that was
yeah.
related to math.
Sorry, I just forgot. Yeah. So I mean, there will be probably a course with him in future where he will cover some of these coding methods. Okay, this is called. So there are many different they have very complex computation, and these are some popular methods for this FEC, okay, which is also called error correction code, or ECC. Now, in all these cases, you have to send some additional bits. If your original packet content has 100 bits, you perform a complex calculation, and it will increase the packet size. It may become, say, 150, okay, or it can be 200 bits in the packet, and then you transmit, okay, and the receiver does not, well, let me show you I mean, very primary level of technique, okay, just to help you get how it I mean, this method is never used, okay, the actual methods are very complex, but this can help you an idea that this type of codings can work. Like, say you want to transmit say only 0 or 1. So okay, so when you want to transmit 0, instead of 1 0, you send 3 zeros from the transmitting end. When you want to transmit 1, instead of only 1 bit, you send 3 bits with values 1, definitely. Okay, now the poor SINR can cause some errors, and the receiver may receive 1 bit flipped. Okay, so it may receive 001 or 010 or 100. One of the bits may get flipped on the way. The receiver will then consider that, well, I should receive all zeros, but they are not. Then let me poll. I have more zeros than 1. So I conclude the reception to be 0. Okay. So even after some flipping of bits on the way, or you get a bit in error on the way, the receiver can decide the correct bit, or it can determine the correct bit. Similarly, when you're sending 1, if 1 bit is in error, okay, on the way, then you can still recover or reproduce the original bit. Okay, and see here, you are sending 2 more bits. So in this case, you can say that I have 2 parity bits. Okay, the number of bits that you add to the original is called parity. So you have 2 parity bits. Out of 3, you have 2 parity bits. Now, now you see that if you send 5 bits instead of 1, okay, in this example, you have 3. If you send 5 bits, then you could allow 2 bits in error for eventual correct reception. Okay, even if you have 2 bits go in error on the way, you can still have correct reception. But that requires that you send 5 bits, but that would be even more luxurious. You see, instead of 0, 1 bit, you're sending 3. So that increases the bits. I mean, it is costlier or slavish. Okay, it actually reduces the overall data rate uh, by a ratio of 3. 1/3 will be your overall data rate. Okay, so the actual coding methods are very complex, where your capabilities are very strong, but the number of bits that you add doesn't have to be that high, but it can still high. Okay, so it is called ratio code rate, the number of actual information bits ratioed with number of bits you are sending. Okay, I mean actual information bits plus parity bits, the total bits you're sending. So in this example, our code rate is 1/3. Okay, and if you had 5 bits instead, the code rate would be 1/5. Okay, now a lower code rate definitely gives you higher reliability. It is more likely that you receive correct bits, but larger packet size, reducing the overall uh, reduction in the data rate. Okay, well, now you actually need to have some balance. You actually need to have some balance. If you have poor radio link, then the code rate needs to be lower for a particular uh, coding technique. All coding techniques are not equally strong, and also their computational time, okay, is not the same. The processing period, the cost of processor is not the same. So there's a trade-off, and you may choose the right coding technique for yourself. Convolutional coding was was a very popular technique for a long period. Nowadays, turbo code and LDPC codes are getting more popular. Okay, at this moment, LDPC, Dr. Rakibul Islam works a lot on LDPC code, and this is found actually very well capable LDPC. Okay, so turbo code and LDPC, they are competing with each other, and different types of environment actually show their capabilities different. Okay, so it also depends on other factors, which may be the right choice of code for your application. Anyway, so for a particular coding technique, the code rate tells you how much reliable it is. If it is a poorer radio link, then you need lower code rate, because more bits can go in error on the way. More bits can be flipped. So a lower code rate or a higher reliability measure you should adopt. Okay, but that comes with the cost that your packet sizes are increased unnecessarily, not unnecessarily, but it is increased, and so the overall data rate will go lower. The target is to have good data rate. Okay, now let's go back to our modulation technique. See, if you go for a higher level of modulation, like in the case of uh, this QAM, okay, 4 QAM or 8 QAM, the separation among the dots in the constellation diagram is, I mean, is quite a bit. But when you go to a higher level of modulation, 16 QAM, then the separation is less. So in this case, if you have poor CINR, there's a higher chance of misdetection, because misdetection occurs when you're confused between the position of two dots, and if the positions are closer, then there is a higher chance of confusion. But that depends on the CINR. The CINR will cause higher deviations. So if your CINR is lower, you should adopt, I mean, greater separations, meaning that lower level of modulation. Or in other words, if you have good CINR, then you can allow higher level of modulation, with the advantage that a higher level of modulation will put more beats in the symbol, in every symbol, increasing the data rate. Okay, like in the case of code rate, if your CINR is good, then you can reduce the code rate, and that will allow the transmission of higher number of actual information bits. So your actual information bits can have higher data rate, or your actual data can improve. But if your decision is not appropriate, if you decide very high modulation rate, considering your CINR is poor, but you are choosing higher modulation rate, or you can see the screen, right? I am moving between slides. Can you see?
Yes, sir.
Okay. Or if you choose a higher code rate in a poor radio link condition, what will happen? A lot of bits will be in error. Then you will have to retransmit a higher number of packets. So that will actually degrade the data rate. Okay, so you're trying to improve the data rate by maybe by increasing your modulation level or lowering your code rate. But if it is not appropriately chosen, then that will rather degrade the data rate, because that will cause very high retransmissions. So there has to be some balance, and very well chosen balance. This is a critical adaptation. Like, as a user moves closer to the base station, okay, we already showed in our previous demonstration that you also, I mean, if you're getting closer, then your desired signal power will be higher, and also you are getting away from further away from the base station, which is retransmitting. So your interference will be lower. Okay, so you're maybe getting closer to your base station, your serving base station. So your C will improve, your I will reduce. So your CINR will improve. So as your CINR improves, then, okay, I didn't tell you what EVM is, I'll later tell you. But as your CINR is improved, you can use higher modulation level and lower code rate. Higher modulation level and lower code rate, right? And that way you can enjoy higher bit rate. Okay, or actually higher spectral efficiency. Spectral efficiency I probably defined in the beginning of the course when we discussed Shannon capacity, how much bit rate per hertz you can use. Okay. On the other hand, as you move further, your CINR will degrade. So, okay, now from a particular position, you have moved further away. So CINR has dropped. At this moment, you are still using high modulation level or low code rate. Okay, so you don't have a good choice of MCS. Then what it will lead to is higher packet rate transmission, and there can be an overall degrade in the bit rate. Okay, so the modulation and code rate should be appropriately chosen. Okay, I will discuss that, but let me tell you what EVM is. Okay, since I mentioned this. Okay, do you see the screen? The same slide again? I'm sorry. You may not. Do you see the slide? Now it is code rate ECC codes.
Yes.
Okay.
Yes.
Okay, you do.
Sir.
Okay, now EVM is so when you have a deviation from the position in the constellation diagram, then you can draw a vector line between the deviated position and the the correct position, okay, where it is supposed to be. So a vector line you can draw, which has both magnitude and direction. Okay. So this is called EVM, error vector magnitude. Error vector magnitude. So once again, at the receiving end, the dots in the constellation diagram are shifted. So as you draw a line between this shifted position of the dot and the actual position, I mean where the dot is supposed to be, when you draw a line between them, you consider a vector, then it is called error vector magnitude. It has both direction and magnitude. No, I mean it's a vector, but its magnitude is called error vector magnitude. Okay, it's called error vector, and its magnitude called error vector magnitude. So when you have higher error vector magnitude, it means that it is shifted more, and so it is closer to the next position, and so you have more chances of errors. Okay, so that can happen with poor CINR condition, as we are showing here. Okay, so here lower CINR will cause an increase in EVM. So you need to choose proper modulation and code rate. Okay, so in the next class we will discuss how you adjust this modulation and coding scheme for cellular technologies. Okay, now any questions?
No, sir.
Okay. Okay, thank you very much. Thank you for your time. Jazakallah.
Assalamu alaikum.
Wa alaikum assalam. Wa alaikum assalam.